All right, good evening, everyone. There's still 2.5 minutes to go, but since the hall is full anyway and we are ready, we decided we'll start early. We'll just still go for 60 minutes, not extended, but we thought we'll start a couple of minutes early. So, right, we actually did this session just an hour and a half back upwards on level 4. The hall was overfull, and when we saw the subscriptions a couple of weeks ago, we were asked to do a repeat of the session in the evening. So it looks like blockchain indeed is generating a lot of interest and is popular. To set expectations, I guess what we're trying to present in this session is just talk about the basics of blockchain first, why the trends are evolving as to why, and then somewhere 10-15 minutes down the line, we are going to get much deeper in the technical aspects of it, right? And then we'll also cover a couple of demos at least. If time permits, then maybe 3 demos. And then towards the second half, we'll cover sort of the AWS angle to it, how AWS views it, how we provide building blocks and what we see in the future. And then at the end, some trends and risks that we see with the adoption of blockchain. Right? So by way of introduction, my name is Shantanu. I have been in part of AWS for a little over 6.5 years now, so I've been here for a while. I'm not from the United States. I'm from Asia Pacific back in India, which, as you can imagine, is a few thousand miles east of here. That's my Twitter handle. My role in the company is I manage a large team of solution architects based out of Mumbai in India for the western region of India. That's my Twitter handle if you want to connect. Anand, my colleague, is my co-presenter. Anand, you want to introduce yourself?
Yeah, so good evening, guys. I'm Anand. I'm an enterprise solutions architect, the AWS team, based out of Mumbai, India. I work with some large conglomerates based out of the western part, and I work with Shantanu's team as well.
All right, so to begin with, right, to start with the 101 of it, right, if you think about it, blockchain, really the concept, and before that Bitcoin, has evolved and started off more first from the financial industry, right, the FSI space and banks. Right? So take a very simple and rudimentary example, which is much more tangible, right? Banking as a business has always existed. We all know about banks, right? And it hinges on this core principle of trust, right? You see banks as a trusted middle party to keep your money inside it, and you obviously trust them, the famous saying that your money is probably more safe in a bank than at your home, right? And so for years, this sort of concept has existed fundamentally. And to add to that, really, the concept of, if you think about it, the concept of having a central authority of sort to exchange goods in form of kind or cash, or in the modern world with debit cards and credit cards, has always existed for thousands of years. Right from when human beings were much more rudimentary in terms of how they exchange goods, there was always this concept of a middle person or a trusted authority. Right? But if you actually have seen articles and follow the web and news, instances of distrust maybe or rigging, including the financial crisis in 2007, has existed, right? So be it banks or investment banking or capital markets, etc., there have been instances of distrust occurring out of this trusted middle party, right? Some of them don't come in the offing so easily. Some of them do come out in the offing. Banking, if you think about, if you actually theoretically just forget the regulations and the laws in place, technically speaking, is actually a very simple business fundamentally, again, going back to them acting as a middle person, right? And they've been very profitable by virtue of the license they carry for years, protected by regulators, and given the volume, they've always sort of been profitable businesses. But technically speaking, actually, if you had a mechanism to leave the middlemen out by a way where you have a trusted distributed network structure, and to do this, banking as a business can be disrupted very, very easily. In fact, in the financial services space, you could argue that banking probably is the simplest business to disrupt. There are other reasons why it's not been disrupted, but technically speaking, it can be disrupted very easily. Now, let's look at a very simple funds transfer process as it stands today, right? So I want to transfer money via my bank to, I don't know, my cousin, let's say, in another country, internationally. What you would typically today do is go online or physically and choose a international money transfer authority like Western Union, pass the money via there. That will then go to a bank in the local country, go to a clearing house. It will then go over the wire all the way to the bank of the destination country and to the branch where the user holds his or her bank account, and the money will get debited and then credited rightfully. Now, this is something we are almost always used to in our daily lives. However, if you think about it, each of these layers adds processing time and cost, right? Because it goes through a series of transactions there. In the back end, there are a lot of things that happen, and it actually adds time and cost. And most international banking transactions today, generally across disparate banks, would probably take at least a few days for the entire transaction to complete, depending on case-to-case scenario. And so, which brings us to the question, to solve these challenges, are we ready for blockchain, right? Are we close to sort of blockchain, let's say, going from experimentation stage or just being something that's cool to going mainstream? Just like most technologies which have been disruptive and leading edge, there'll always be skeptics, right, who kind of doubt whether this will actually go mainstream, or what the risks are, what the laws and regulations are, et cetera, et cetera. And so, so let's look at what's going on, right? We would argue that if you look at the timeline, right, and evolution, we're already seeing companies in the experimentation phase, to give you examples. So just to sort of do a bit of a history class, back a little more than 20 years ago, Nick Szabo came up with this concept of smart contracts, which we'll kind of cover in the second half of our presentation, right? We obviously have this famous story about 8 years ago where the concept of blockchain was really evolved back in 2009 by Satoshi Nakamoto. We now are seeing really industries outside of the FSI sector which are starting to experiment with blockchain, right? Starting from, let's say, retail giants like Walmart and Nestle in US, building a blockchain consortium to see what applications they could develop out of the blockchain framework. Back in India, we have this large conglomerate called the Bajaj Group, which is a family-owned business, and Bajaj Electricals, which is one of the child companies doing appliances like toasters, microwave, and stuff like that, huge in the B2C space. They've kind of started operating out of blockchain framework network to run their vendor financing solution for their partners. And there are other companies like Samsung and Maersk, so very, very broad, manufacturing to container services in the marine insurance space, et cetera, et cetera. And there's talk in the industry, really, if you read articles, that this should really, people believe that this should really go mainstream in the next 3 years, give or take one year additional or lesser, to really having serious applications even outside of FSI industry in the blockchain space. So what is blockchain? How many of you are sort of already deep in the blockchain space in some shape or form? Okay, some of you. So a blockchain, typically in the simplest form by definition, is really a growing ledger of all the transactions that happen. It's obviously distributed to kind of mitigate the issues of a central authority that we spoke about initially. There are other tenets that you can see, like decentralized, trusted, secure. I won't cover them right now, but in Anand's presentation, you will know as to why it's secure and why it's automated and much more efficient, and why it's immutable. The Bitcoin thing that was sort of the first application of blockchain is a public network. It's completely permissionless. So by default, it can be shared publicly. Again, this is not completely true because there are other frameworks of blockchain where you can have permissions come in, so it's not completely public. Now, before we proceed, this is something of a question that we always get, especially for novices. People tend to think that Bitcoin and blockchain are the same thing. That's not true. Obviously, in the last 12 months, they've diverged. Bitcoin is really, to reiterate, a cryptographic currency, a digital currency which is extremely popular with speculators. It's very, very popular in developing and emerging markets, and a lot of you probably have interest in Bitcoin. Blockchain, which is what we're going to talk about in more details today, on the right-hand side of your screen, is really the distributed ledger technology with applications in domains far beyond the FSI industry, so things like smart contracts, et cetera, et cetera. So what would, let's say, taking the same example, what would a funds transfer across, let's say, banks or international borders look like if blockchain were to come mainstream, right? So as a rudimentary example, if I were to, again, take the same example, I go to a bank, online transfer money. Instead of having all those steps and instead of having a clearinghouse, you would typically have a chain of a blockchain network with multiple nodes. And each of these nodes would have a distributed ledger, which kind of verifies this. And then each of the nodes can be considered as participants, including government firms, security exchanges, manufacturing firms, et cetera, right? And so, as you can see, it can be completely automated and much more efficient without having a central authority in place. So now we'll kind of, let's sort of deep dive into how a blockchain actually looks and how are blocks actually formed, including a couple of demos. Anand, you want to continue?
Yeah. So we talked about three main aspects of a blockchain, right? Fundamentally, it's a trusted ledger. it's immutable, and there has to be some consensus mechanism by which all the nodes decide that a particular transaction is valid and it should be committed across a ledger. Since you don't have a central database where you are actually storing these transactions, that's what you have today. You're trying to split it across multiple nodes. These are distributed nodes, and these, in case of Bitcoin, it's probably millions of nodes. So the problem becomes, how do you ensure that consensus happens between all these nodes to say that, yeah, this particular transaction should be committed? To understand that, first we need to understand hash. Right? If you go back to your computer science 101 class, you probably learned what a hash function is. A hash function, in very simple terms, takes an input, runs an algorithm on it, and gives you an output. The output could be a 128-bit string, a 256-bit string, depending on how secure you want your hash to be. If you have implemented authentication systems, you probably know you store a password. You don't obviously store a clear text password. You would store a hashed password, right? So the way you create a hash password is you take that string, the password, pass it through a hash function. It will give you a string, and you store that. So unique property about a hash is, for every input, it will give you the same output. But taking the output, you cannot derive the input. So I can go from input to output through the hash function, but I cannot give that output and get the input back. So they are critical to the way blockchains really work. Now, what does a blockchain really look like? If you were to go in the physical world, the physical ledger, you would have a set of transactions. You would keep those transactions recording on a page, and a set of those pages would form your ledger. So if you were to think about that example of credit and debit, a credit would be one transaction on that ledger, a debit would be another transaction on the ledger, and it would sort of follow through a set of pages. Similarly, consider this. Each block here is a page, right? And all these blocks together form your ledger. Now, how do I link these? Now, in each block, I would take a set of transactions. For example, since a block is limited by the size, in the Bitcoin world, it's 1 MB, but they're looking to increase it to 5 MB. In other frameworks, now Bitcoin is an implementation of a blockchain, but there are other frameworks where you may have block sizes which are different, right? But a set of transactions gets hashed. So in my previous example, I showed you how to create a hash. There may be a set of transactions. All of those you pass through a hash function, and you generate a hash value. You take that hash value, you commit it in that block, which is the block hash value. Now, I want to link this block to the previous block. So I take the previous block's hash and store it. So that way, I can keep traversing it all the way to the front, right? So it forms sort of like a linked list with a previous node pointer. So that's what I'm showing here. Block 17 has its own block hash. Block 17 also stores block 16's hash. Similarly, block 16 stores block 15's hash. Now, why do we need to do this? And that comes back to the point of security, which I'll show in the demonstration. So that's what I mentioned earlier. A block is linked to the previous block through a previous block hash value. Now, if someone wanted to go and change a transaction in a previous block, let's say if I want to go and change the transaction in block 15, it would change the block hash value because I'm taking a set of the transactions in that block, passing it through a hash function. It will obviously give me a different hash value, right? As soon as I change that hash, it's going to cause a problem in block 16. Because block 15 hash changed, I'm storing that previous block hash value here. So that got invalidated, which means I have to go and recompute that particular block hash value. And that's the nicety about a blockchain. As soon as something changes in a block, or someone tries to change a transaction in a block which has already been committed, it sort of invalidates all subsequent blocks. And that's the immutability part of the ledger. So transactions are logically, in our case, the funds transfer example, the receiver, the sender, the data, right? So in this case, I have a transaction where I have the transaction ID, I have the originator, the recipient, and a timestamp at which it happened. So all of this information is what I'm trying to store in my ledger. So that's great. So I have a set of transactions that are coming in, and all of these transactions have to be committed in the ledger. How does the blockchain framework decide which transactions should be committed in the ledger and who should commit this? Because it's a distributed system, there has to be consensus among all the nodes that, yeah, these transactions are valid and you can actually go ahead and commit it. So this is what happens in the Bitcoin world, but it's pretty similar in other frameworks as well. A set of transactions is submitted in the memory pool. So let's say I have 1,000 funds transfer transactions that are happening. The system will say, I'm going to take these transactions which are not committed. They are not in the ledger yet. It will bunch a set of transactions. Let's say it will bunch 15 transactions and submit it to the set of nodes. Now, within the nodes compete with each other to commit this set of transactions. So how do these nodes compete with each other, right? Each transaction, they will generate a hash value. Going back to my example, they will pass it through a hash function. So for each transaction, they will take that data, pass it through a hash function. They will generate a hash value. So in this case, I have 6 such transactions which are being expected to be committed to a block. So I'll get 6 such hash values. But the ultimate objective is I need the block hash, right? So I have to combine all of these 6 transactions and find ultimately a single block hash value. So I sort of run them through, I combine hash values 1 and 2. I do that same thing for 3 and 4, 5 and 6. I get 3 hash values, and then I combine all of these. Then I get 1 single hash value. Now I have 1 hash value for this block. What I have done is I have taken the previous block's hash, I have taken the current number of transactions, and I have taken the timestamp and created a hash. Now all of these have to go in a block. The concept of mining comes into play here. Because you have nodes that have to decide which, who goes and commits this, they compete with each other. The way they compete is they look for a value called nonce. It's a random number. That nonce value combined with this block hash should give me a hash which has a number of leading zeros. In the Bitcoin world, it is, let's say, 6 zeros. A demonstration here probably will help explain this. So I was talking about hash, right? So this is the property about hash. If my data is called this is my data, as you can see, as I keep changing my data, my hash values keep changing in the hash block. So with that in concept, let's go to how a block looks like. So my block this is my data, right? The hash value, if you see there, is 22471F. Now I'm looking for a hash value which will be leading 5 zeros. So all of the nodes are trying to solve this problem where they can get a hash value with leading 5 zeros. But obviously this nonce value is not giving me that. They have to just do this brute force, right? So they will just keep trying, maybe 10,000, doesn't give it. Let me try with 7846. Oh, 7846 gives me a hash with leading 4 zeros. So every miner sort of is doing this brute force. They're just trying with a set of random numbers and trying to come up with a hash value of leading 4 zeros. In some networks, it may be leading 6 zeros. In some networks, it may be leading 10 zeros. Now, computationally, they are spending a lot of power and space and cooling, right, to do this. So since it's an iterative process. So once they find this nonce value, they will broadcast it on the blockchain network, saying, I, as a mining node, I found this nonce value, and I have found the answer. Now, to do that, the Bitcoin, it will broadcast it, obviously. Everybody else can take that nonce value, append it to that block hash, run it through the hash function, and verify that nonce value, because I could just broadcast any nonce and say, hey, I found the answer. But everybody else has to verify. And that's where the consensus comes into play. Consensus from all the nodes saying, yeah, you were right, you found the right nonce value, you can go ahead and commit this block. And they will also say, yeah, so I'm not going to work on this problem anymore, I'm going to pick up the next set of transactions. Now in the Bitcoin blockchain, every miner is rewarded if he finds this nonce value with a certain percentage of a Bitcoin. And that's the incentive for them to keep this network running, right? Otherwise, who else? Why would they want to spend their computing power to solve this problem? So that's the incentive for them, that they will get a Bitcoin. In Ethereum, same thing happens. So this process of finding this nonce value is called proof of work. That's a consensus method. There are other consensus methods as well, but proof of work is really very expensive, because now you have all these mining nodes, everybody is trying to solve and compete with each other to find this nonce value. And you could bring, you could have pools of computers come together, or you could have miners from countries where electricity is highly subsidized, and they could form mining pools there, and they are the ones who get outsized rewards every time, and others are starved. So it's not a great solution, obviously, having proof of work as your consensus mechanism, if you will. So let me switch back. Oh, before I switch back, I wanted to show, so you got the concept of a block, right? So that's what mine does. So I'm going to go back here, and let's say this is mine. This is what the nonce is. And if I say mine, so that's what miners are doing. When I clicked on mine, it found 7846, right? So that's what miners are doing. They're constantly trying to run through a set of nonces to find the hash value. The network defines what the hash complexity is. The complexity could be 5 leading zeros, 10 leading zeros. And in Bitcoin, it keeps, as you mine, the complexity increases, because they want to make it harder and harder for you to mine from the network. And that's why the coin price increases. So now with a block committed, you go to a blockchain, right? So if I were to do this, I mine here. As you can see, it will mine. It found a value. It has the hash value. Now this hash value has to be stored here. Because I changed the data here, this particular block became invalid, right? I changed, it was empty here. I added some data, and then I had to mine. I mined. I got a hash. Now this hash has to be put here, but this block is invalid. So I click on mine again. It will mine. It will find some nonce value. And then it has taken this hash value and put it as its previous node. So if you go back to that mental map of how the blockchain links, it's basically taking previous hash values and adding it to the subsequent blocks.
Can I ask a question?
Yeah. Can we hold questions until the end? On this? Okay. Yeah, so you cannot. So which is what the idea is, that you could not change a transaction which has already been mined. Because if you try to go and change the transaction, the block will get invalidated, and you as a miner will have to go and fix all the subsequent blocks as well. And I have a slide coming up which will explain why. So I hope proof of work is clear to everyone. So proof of work is, it's a set of transactions that are waiting to be validated, and it's picking a nonce value, right? That nonce value is nonsense. That's what it stands for. It's a nonsense value. It's not used anywhere. But that's the answer for everybody to validate, saying, hey, I have found the answer. Can you please validate this? And if it is wrong, obviously, I don't get the reward. So verification is easy, but proof of work is hard. So, and to your point, so why can't you cheat in this system, right? I can, if I wanted to cheat, I can bring in a supercomputer that comes in and tries to go back to block 74 and maybe add $1 million into my account. right? I want to go into block 74 here. Block 74's transactions, I want to add in maybe a few dollars into my account or change the data in that block. Well, if I do that, I invalidate that block. I also invalidate block 75 because block 75 has block 74's hash. And I need to go fix block 75, then I need to go fix block 76. I need to keep doing this up till, in this case, the nodes are working on block 91. Now it takes about 10 minutes today in the Bitcoin world to mine. So that's how complex it is. So they have to keep, it takes about 10 minutes for a node or a mining rig to find the nonce value. So if I were to do this, if someone were to go back, in the Bitcoin world it's extremely difficult because I would have to go back in time, fix all these block hashes, and then come back here until by that time someone else has already added a few blocks. So I'll always be trying to catch up. So that's why it becomes really difficult in a blockchain to go and change something and be not noticed. So if you hear anything about, oh, there was a security issue in a blockchain, it was probably not that someone went and invalidated a block. It may have been something else. So I talked about proof of work. So Bitcoin obviously started with proof of work. There is another framework called Ethereum, which also used proof of work, which is basically miners trying to find a nonce. But they have moved from proof of work to proof of stake. And proof of stake is an alternative consensus mechanism. Here, not every node is allowed to mine. There are special nodes who have a certain stake in the system who can mine. For example, if I want to mine, I have to put something on the table. I have to say I have so much Bitcoin. Based on the amount of Bitcoin or Ether that I have, I can mine. So if I were to be sort of malicious, I would also lose, right? If I want to break this system or if I want to cheat in the system, since I have a stake in the system, I wouldn't be a bad actor. Whereas in the proof of work, there could be bad actors. For example, I gave that example of people coming together and forming mining pools and taking outsized profits and always starving others. Whereas proof of stake sort of keeps the system good, keeping good actors in place. So it acts as a check and balance. So proof of stake, there is no block reward, but miners take transaction fees. Whereas in proof of work, there is a reward that a miner gets, which is usually a Bitcoin. Whereas here, it is more of a transaction fee that they get, which could be a fixed fee. Apart from this, there are other consensus mechanisms as well. These are not the only two mechanisms. There is a framework called HyperLedger, which uses a consensus mechanism called PBFT, which is practical Byzantine fault tolerance. You can read up about fault tolerance. It's a very interesting problem. There is proof of elapsed time. There are alternate consensus mechanisms as well. So it's not necessary that you have to pick one of these. So that brings us to the point of understand. So now we have an understanding of what a blockchain is, how are blocks committed to the blockchain, what are the different mechanisms, consensus mechanisms in place, because consensus is what really forms the core of blockchain. I mean, decentralization is great, immutability is great, shared ledger is great, but consensus mechanism is what really differentiates all of these networks. So you have permissionless blockchains, you have permissioned blockchains. A permissionless blockchain is anyone can be a part of that network. So for example, Bitcoin, even you and me can be a part of that network, right? Whereas with something like HyperLedger, it's a very permissioned blockchain. So only certain nodes can be a part of that blockchain network. Only certain nodes can be committers on that ledger. And there will be a certain node that will decide randomly that this particular node can be the committer. What that allows them to do is increase the scale of transactions that they can process, because it's limited, it's not miners coming in and trying to compete. And that's why the Bitcoin network is slow today, whereas some of these other networks like HyperLedger, more permission networks can be faster. But obviously, it goes against the point of decentralization. You're again going back somewhere in the centralization space. Depending on your use case, for enterprises who want to form private consortiums or maybe a closed network, a HyperLedger or Ripple can be a more viable solution. So we'll talk about contracts and how that applies in the blockchain world.
Right, so we spoke and started off and gave a lot of examples from the financial services industry, more transactions and funds transfer, right? But when we were talking about blockchain probably going mainstream in the next 3 to 4 years, this is what we meant in terms of applications with the blockchain framework, different applications providing use cases beyond FSI and much more across multiple industries. So let's take another simple example of, as simple as selling a car, for example, a car transaction, right? Today, if someone wants to, let's say, an example of a Bob and Alice. Bob is the owner of a car. The car has got old, and let's say he wants to sell it to someone. The way it would work is there are obviously central authorities still in this scheme of things, like a motor insurance company, a motor vehicular registration company, a legal notary, etc., and many others to kind of do a bit of manual work before a car sale can be registered and considered as valid. And there'll be a bit of paperwork as well. So obviously not super efficient, but that's how it stands today. In the future world, potentially, when you're talking about smart contracts, right, using blockchain or distributed ledger technology, we could probably look at something like this at a high level. So Bob, as a first step, would probably identify himself on the blockchain network using his blockchain address. He would then end up signing a smart contract where he would basically define the conditions or prerequisite of the sale of his car, which would probably include, among other things, the cost at which he's putting up to sell the car. Let's say 20,000 euros, for example, right? And next, what he could do is he could drive his car, leave it in a garage, and ideally the car would have a smart lock, which can only be opened with an access key. Right? Now, somewhere in the digital world over the internet, Alice is looking to buy a car, a second-hand car, finds this car meeting her requirements, right? So what she could do is sign this smart contract that Bob has put up with her private key. She would then use her blockchain address to actually transfer 20,000 euros to the destination account. And once this happens, it then triggers the blockchain network, right, where all these nodes actually ensure whether Bob is the actual owner of the car and where the amount, which is 20,000 euros in this case, and other prerequisites of the sale have been fulfilled correctly. And if it has, then Alice would probably ideally get an access key or the access code to open the smart lock of the car which is parked in the garage, and in parallel, potentially, have the 20,000 euros deposited and reflecting in Bob's account. And so then she could go in, punch in the access key, and then walk away with the car. Right? So no central authority, completely distributed and automated and much more efficient. I know it sounds a little futuristic, but I think this is how it would work with smart contracts. And you could imagine this to be the equivalent of any other use cases as well. We just took a car sale example just as an example to keep it simple. Now, coming to AWS, right, sort of the AWS plane, this, as usual, as has been our sort of philosophy for the last 11.5 years, we try to democratize technology and any play to ensure that it is easy to start with. And whether you're a one-member startup or a well-funded organization, it's as easy for both of you to kind of access technology and make it simple for you. And second, we try and stay neutral in general, so we're not really looking or vouching for one protocol or a particular blockchain framework over the other. What we think we'll do, at least to start with, is give you our suite of services and building blocks, over which customers and consumers can then build DLT technologies, distributed ledger technologies. To look at a couple of very simple architecture diagrams, and I'm kind of going fast because I want to sort of save some time for the demo. Ethereum is something that Anand spoke about, generally by default permissionless, but you can configure it to have certain permissions. It's one of the frameworks. You could typically choose, in the simplest form, our infrastructure building blocks, which is any one AWS region, form a VPC within it, and then have your normal web applications on an API within it. And then what you could typically deploy is something called as EVM, or Ethereum virtual machines. These typically would be your nodes in that blockchain network, which are basically ensuring validation of your funds transfer or the sale of a car and so on and so forth. Right? You would access it just like you would access multiple web applications, and most of these applications are typically microservices. So you could use our ECS service, which is our Elastic Container Service, if there's Docker, or as was announced in Andy's keynote today morning, we have also released a Kubernetes managed service to manage Kubernetes clusters. So depending on what containers they are, if it's in a container form and microservices, then you could actually use this ecosystem to kind of deploy this on the cloud. Another example would be, which is very popular today, is mobile wallet, right? So everyone uses wallets, especially in the emerging world where we come from, where it's very, very popular. And so you would again go the same route, where you would use fundamental framework of AWS, which is a VPC and network, different subnets. And then you would have, let's say, something as a hot wallet application, and an exchange microservice, which processes all the transactions that are initiating from the hot wallet, and then forwarded and executed and validated. Most consumers that use this, we have seen, like to keep a cold wallet as well. So imagine the cold wallet as your savings bank account, right? Which is having a private key and all the data there, and only when they want to transact, they actually take that to a hot wallet, transact, and then bring back the funds to a cold wallet. Being a very financial sensitive sort of application, because you're actually transferring money here, you could use things like, let's say, Cloud HSM, which could help with two-factor authentication, and you can store your keys there. You could use our managed Docker service in form of ECS or EKS now. AWS Batch is a service that sort of can help you batch some of these transactions, and you could run an end of the day batch job to kind of get a list of transactions, or during regular periods a day. And then finally, if you want to send push notifications for a transaction when it's successful, or a notification via email or SMS, you could use something like Amazon SNS. And then after each transaction or certain transactions, the smart contract associated with it can be then pushed across and executed as well. So now let's look at another sort of demo. I guess you have a couple of them if you have time, of a mortgage sort of process, that how it would work. Let's say here.
Yeah. So I have two demos. First one is on Ethereum. The use case is, I have a homeowner who is looking to buy a home. So he goes to the bank. The bank is the second party here. Once you get the loan, you obviously have payments to be made. You have tax payments, property tax payments that you make. You also have an insurer for your home, so you make insurance payments. And all of these form your blockchain node network. Everybody has complete visibility into the set of transactions that are happening. And at the end of the day, if you want to have a smart contract where once you pay off the loan, the title probably automatically moves in your name, right? Today, you may have a bank, which is the guarantor, and that's why they have the title. It's a shared title. So that's what the demo we are going to look at. The homeowner will come in. He will initiate a loan contract. It will go to the bank. The bank will then approve the loan. After he approves the loan, at every step here, all of these are sort of transactions that are being recorded as blocks in the ledger. And since these are immutable, and since it's a shared ledger, everybody has visibility into it. As you make payments, each of those payments, again, are blocks that are committed on the ledger. And once the payoff is done, it sort of whatever smart contract you want to execute, you could do that. So here's our demo. So I have homeowner, I have mortgage holder, who is the bank. I have the insurer, and in this case, I have IRS, but this is your property tax holder, right? Everybody has an account address, as you can see. It's a hex. It's a hex number. So I start and initiate a loan contract. As I initiate a loan contract object is made, and that transaction gets recorded on the ledger. So if you want to inspect the ledger, this is the tool that allows me to look at the ledger. So what transaction happened? So if I just refresh this, as you can see, a block was added, right? If I click on the block, it will sort of give me details about, since I'm not running a set of mining nodes, because it takes time. In this demonstration, I'm just showing that as you are submitting the transactions, they're directly getting reflected in the ledger. But ideally, what would happen is, as soon as I submit the transactions, there would be a miner that would run, that would validate. There would be probably multiple miners who would then validate, and then it would get committed in the ledger. But it gives you visibility of the transaction. It will tell me what was the transaction hash, what was who did it come from, and who did it go to, what was the input value for that. So this is sort of the transaction data. Gas, so on Ethereum, to execute a transaction, you need to have some Ether, right? It's like virtual currency that you need to have in your account, so that you don't just randomly send transactions to the system. So not everybody is just randomly sending transactions and everybody's sitting and mining. So you need some gas in your account. And if you are setting it up by yourself, the system will keep generating the Ether and gas accounts for you. But ideally, you would, if you create a private network, you will have control over this. So I have submitted I have initiated my loan. Now I need to submit it. So I'm going to just put some details here. My purchase price is 500,000, let's say. I'm going to take a loan for 120,000. I'm going to calculate it. And right now it's in the initiated status. I'm going to submit the loan. Once I submit it, it goes into the submitted status. And the mortgage holder, which is the bank, has received this loan now, right? He needs to approve it. So he's going to look at it. He's going to look at the loan contract. What are maybe possibly do a credit check and all of that. And then once all of that is done, he's going to approve the loan. As I'm doing these steps, you will see that the block explorer we are adding more blocks. And these are things that are being added to the ledger. So these are, again, immutable records, so you cannot go back and change any of this. Now, let's say our bank has approved our loan. I go back, the homeowner. Now it's time for the homeowner to start making payments. So let's look at monthly payments. He's going to make a first monthly payment, and he's going to send 3 different monthly payments, right? He's going to send one to the mortgage holder, one to the insurer, and the other one to the tax authority. So I have sent all these to these different addresses. So the mortgage holder has received his first payment. The insurer has received his first payment as well. And all of this, again, is getting reflected in our ledger. So the ledger is sort of immutable. It is growing now. Transactions are being added. Finally, when the homeowner makes or does a complete mortgage payoff, he will send these, and these also get recorded. And so the mortgage holder now sees that, okay, the outstanding balance is 0. Insurer also sees that his balance is 0. And again, these transactions also get recorded here. So it sort of gives everybody the view of what transactions were done. Everybody has the same view of that ledger. There is no central authority now, but it's nodes that are forming the consensus and recording these transactions. The next. Yeah, it's unconfirmed because I'm not running a miner. Once, if I run a miner, it takes a while for it to run, right? But all these transactions, there would be miners who would be mining. So these nodes that I designate as miners, in this case, I would designate a miner as the bank node could be a miner. Right? They would confirm, he would mine, he would commit that transaction to the ledger, and the others would confirm. So right now, I don't have those nodes running. I'm just using a simulator. There's a test RPC network that you can use to simulate. So I just showed you that. The next one is on HyperLedger. So this is the other permissioned, if you may, the permissioned blockchain, right? Here, you can define more granular rules as well on access permissions and who can be a part of that network. So here, I'm just showing you, it's a simple asset transfer application called Marbles. The application uses 2 peer nodes, and these 2 peer nodes are called endorsers. So HyperLedger as a framework uses a concept of endorsers. They're more like your validators, if you may. They cannot commit anything to the ledger. They are validators. And then you have the ordering service, which can commit transactions to the ledger. And then there is also a certificate authority, which gives you identity access for these nodes. So I'll show that demonstration now. Let me just quickly log in here. I think I'm having issues with my demo here on this one. So I'll, just in the interest of time, I'll skip to the landscape for the blockchain technologies, right? So in financial services, what we are seeing is there is a very large ecosystem of companies that have emerged around the blockchain frameworks, right? So for example, you will see hot and soft wallets, which is an example of wallet exchange that we showed. There are merchants, there are payment systems that have been built, there are capital market use cases, and a lot of them are using either built on Bitcoin framework or they're using Ethereum, but there's a lot of momentum around HyperLedger as well. Again, with any technology, there are risks that you need to consider. We showed you the timeline of where we are today in terms of adoption. It's still in the experimentation phase. And when you're in the experimentation phase, there are different risks. You have standard risks, things like strategic risks. What kind of framework should I choose? Should I choose Ethereum? Should I choose HyperLedger? Should I choose R3? There is something called R3 Corda. There are a lot of competing frameworks today in the market, but they may be apt for certain use cases. For example, R3 is very good for financial use cases. HyperLedger can be applied across industries, supply chain, energy trading, asset management, whereas Ethereum has a very limited tooling, but it's quite powerful. It allows you to build smart contracts. So depending on what use case and what industry you come from, you may choose a specific framework. The other one is regulatory. If you are in regulated industries, you may have certain considerations that you have to look at when using public versus permissioned blockchains. The other one is things like your integration with legacy systems. You have legacy systems, systems of records that need to be integrated with something that you bring, which is decentralized. How will those work? And maybe your SLAs may get impacted if something adverse were to happen. So those are general risks that you would anyway consider when adopting a new framework. There is a pretty vibrant partner ecosystem that's forming around the AWS blockchain offerings. Basically, we have companies like Intel who have looked at the sawtooth and deploying HyperLedger on Intel AMIs. There is PwC that's doing projects at customers. There is Samsung SDS that's also doing HyperLedger-based projects. We are looking for partners who have unique use cases around supply chain or healthcare or financial services for proposals to build repeatable solutions. And so you may want to look at partner/blockchain on aws.amazon.com to see how you can add value in this system. And that was my last slide. Hope you found this session useful, and we are open for questions. Yeah, go ahead.
For Bitcoin, how many nodes have to validate a transaction before it's considered valid?
So,
So one node finds the nonce, and then the rest validate, but how many have to validate the nonce?
so I think he's the Bitcoin expert over there.
So I just wanted to in the previous session.
Yeah.
I've been involved with Bitcoin since 2012. I'm very active on the BitcoinTalk.org discussion forum, answering people's questions.
and helping them learn about Bitcoin. So if anyone has any Bitcoin blockchain technology specific questions, I'd be happy to talk with you and answer any questions and help you understand as much as you'd love to understand about that.
Yeah, thank you.
Anything outside of Bitcoin, I won't be able to help you, but I'll be standing just outside here, and so these guys can answer all the other blockchain questions without me interfering.
Yeah, so we were trying to sort of demystify, right? We didn't want this to become a Bitcoin talk. And so that's the whole idea of this talk, that we wanted to have, when you go out, think about blockchain as a much larger platform rather than just Bitcoin, because Bitcoin is an implementation of a blockchain. Yeah?
Actually, a question for both of you. One, you showed the banking, how it would look like. So my question to you is, why would I need the bank? Why would I actually need to go to the bank, then go to the network, then do it, and then go to the other bank? Why doesn't I go directly to the bank?
Yeah, which is what Bitcoin is doing today, which is what the... Yeah, Ether or Bitcoin or any cryptocurrency, they're trying to bypass banks. But there is still, banks have to figure that out. So what other value-added services they're going to provide, right? But banks are trying to form consortiums where they feel that there is a lot of regulatory concerns still, right, around Bitcoin. It's not clear yet how that is going to go. So banks still have, there is still the whole licensing aspect that banks can still control. And, I don't see a world where we won't have a bank, but there is cryptocurrency that is there that will continue to stay. Maybe banks will adopt cryptocurrency and still offer value-added services around cryptocurrency.
But you're right, in the ideal world, in the very near future.
In the ideal world, it would be just peer-to-peer, so you wouldn't have a middleman at all. So ultimately, I mean, in the Bitcoin world, because there is a incentive, it's a different thing. But it would be like transaction fees only. Miners would get transaction fees, and that's where it is more of proof of work is very good in Bitcoin. It's applicable more in Bitcoin, and that's why they move to proof of stake or maybe other permissioned ledgers where the incentive is random for nodes and there is a fixed transaction fee that they get. Yeah. Yeah.
For proof of stake, how do you create Ether in that? How is Ether created in that?
So I'm not an expert on proof of stake, but I believe that it will be more applicable in Ethereum. I'm not sure internally how they moved from proof of work to proof of stake and how the mining, how the rewards are assigned to a specific miner. But it's turning more into a transaction fee rather than it's a fixed transaction fee. I think there was a question over there.
Actually, my comment on these miners, that seems to be maybe not the most egalitarian ecosystem because, like you pointed out in the presentation, Mr. X has, a supercomputer with 1,000 CPUs and millions of cores. They're going to be able to get that 5 zeros before anybody else.
Yeah.
So that may not be the most.
Which is where the proof of work, that's more for the proof of work, right?
Yeah,
so.
In a proof of work, seems to me that you have a closed consortium, and that to me is almost like a clearinghouse in today's world. So it's not like you're trying to invent something new. It's almost like once you get this closed ecosystem with not the miners, but in this permission ecosystem, they are the ones that are kind of like driving the ball.
Yeah.
Okay, so how do you prevent? I mean, in a perfect world, there's no transaction fees. It's just.
Well, that's why Ethereum moved from proof of work to proof of stake, where in a proof of stake, if a bad actor, like a 51% attack is being done, it can impact them as well.
One more thing. When you have bad actors, I mean, in that type of environment, you're on a kind of like a bad boys list. I mean, if they are doing something that is surreptitious, okay, they can't be in the inner circle. They've had their chance. So that way you have some sort of self-regulating body to make sure that everyone's playing according to the rules.
Yeah.
And that way.
Which I think in Bitcoin it happened. There was a 51% attack that was done a few years back, but everybody else got together and then they thwarted it. So it has happened before. A few questions here. Yeah. Yeah.
So we have differentiated in between public blockchains and private blockchain. So if it's a private blockchain, you have given an example that we can spin up an within Amazon VPC instance, and within which we can instantiate private blockchain. So in that case, if that's considered one of the nodes, should the data miners be on that VPC to validate that transaction future down the line? So everyone, let's say a bank, a financial institution spins up a Amazon instance, has a VPC. So people have to be within the VPC. Again, client is not on the VPC.
Yeah.
The financial institution is in the VPC. So VPC is external to the internet. So how would, in this case, people validate the transaction?
So in that case, it would be more of a consortium, right? The consortium itself, if it's a bank would come up and have a consortium of other banks who have formed a blockchain network just to reduce the transaction costs for transfers and increase the speed at which they transfer. So they would designate miners who would say only these miners can actually mine and validate the transactions. So it's more of a closed network.
So all of the banks should stay within.
Yeah, so there are examples. If you go online, you will see things like Prime Chain. There are banking consortiums that have happened, basically to answer the whole cryptocurrency, wave, right?
Yeah, I was finding a use case where using AWS to scale
Yeah.
this VPC network.
I mean, you could do like cross VPC peering and have resources outside of the VPC, but they are trusted. So you could have miners over there as well in other VPCs, but they are trusted. We'll take last question because we have to end. There's the next batch that's coming.
So when you have a contract on a blockchain, what happens when that contract is violated in some way? So for example, the mortgage example, they're late on payments. So now their payments are behind, now there's more interest, there's things have changed about the contract. How do those changes reflect in the blockchain?
So you could define whatever rules you want, right? If you default, I'm going to penalize you, or I'm going to, here's my set of actions that I'm going to take if you default on my loan for 3 times. All of that are codified in a contract. All of those are codified things in a contract.
In the contract, if you do this, successful, then this thing happen. If you are getting default, then this thing happen. So all clause will be in the.
It's like a program, and
Can I ask one question?
yeah. Last question, sorry.
So you have mentioned that certain technology uses Ethereum framework or blockchain framework. So they are basically using those technology or actually using Ethereum blockchain?
So they have implemented distributed app using Ethereum API interfaces. So they are using Ethereum,
Ethereum blockchain or
a private network. You can create a Ethereum private network.
yeah, that's what I think private version of Ethereum. That's what I'm.
So you can create private networks within Ethereum itself.
Within the public block.
Yeah, so with using EVMs, using the Ethereum virtual machines, you can create your own private network.
Within their blockchain.
Yeah, it's nothing to do with their public blockchain. You can create your own private network as well. Yeah, other than Ether itself, yeah. Okay, thank you guys.